perform operations like inserts, updates, deletes, and to query the data in our database. So to add records, we will use the insert command, which is quite simple. You have insert, followed by, this is optional as well, followed by the optional keyword into, followed by the table name, like into students, and then you have an optional list of columns. Yeah. For instance, here, SID, CNP, last name, first name, and age. You can omit, but it's good style to be explicit about column names, because if you don't, so if you omit this one here and you have this statement that you want to reuse multiple, maybe at some point the structure of the table will change. You will, like, for instance, add a new column. So then such an insert won't work. You will get an error, right? So it's a good idea to be explicit about column names in the insert command. All right, after the column list, you have the values keyword followed by, between parentheses, a list of values. Yeah, you need to list values in the appropriate order so they correspond to the columns in the columns that follow after the name of the table. Now we'll see this one after we discuss queries, yeah, because it involves a subquery. So it's very simple to add data to your tables. You can also change existing records with the update command. Now you have update followed by the name of the table, and then you have the clause in which you can have multiple, like column equals, multiple constructs of the form column equals, and you have some expression separated by commas. Like here we have update student set age equals age plus 1, and maybe comma, first name equals something else, and so on. And then we have the optional where clause. This is optional. That is, if it's missing, if we only have this part for the update command, then this means we will change all the rows in the table. But if where is present, then where is in fact evaluated first. First, we will locate all the rows where CNP equals something. Now, CNP obviously would be a candidate key. So in this case, we would locate the row where CNP equals something, and we will update only that row. And finally, to remove records, we have the delete command, which goes like this: delete from table name, followed by the optional where clause again. So if we have only delete from students, this means we are deleting all the records in the students table. However, the table continues to exist, so we can add other records, or we can change its structure. But if we have delete from students where name equals Popescu, then we will first locate all the rows where name is equal to Popescu and remove only those rows. So these are quite straightforward. Yeah, insert, update, and delete, allowing us to add to tables, to change existing data in tables, and to remove data from our tables. All right, and now we're going to cover a couple of, because we saw the where clause that we can use to filter out the rows that don't meet a certain condition and focus on the other ones. So let's see a couple of conditions that we can use. These can be combined with, of course, parentheses and or, and not. So the simplest of all is obviously this one. You have something like expression, comparison operator expression. Delete from students where SID greater than 5. So here an expression is simply a column name. Here it's simply a number. But you could say where SID time, I don't know, SID plus 2 greater than something, an expression, 5 times 3 plus, I don't know what else. Then we have this special operator between. Expression between min and max, valmin and valmax, or not between valmin and valmax. Like, for instance, delete from students where age between 20 and 30. That is, where age greater than or equal to 20 and age less than or equal to 30. Or delete from students where age not between 20 and 30, with the obvious modification to the meaning of the operator. All right, now we have this special construct is null and is not null that we use to test if a column in some row has the null value. We don't go and say where L name equals null. If, for instance, because null one more time means unknown. If I don't know, I don't know Ionescu's age, and I don't know Popescu's age, they're unknown, this does not make them equal. We'll talk about ways of controlling the behavior of the equals operator when dealing with nulls in Transact SQL in a subsequent seminar. But for now, we always use this construct, is null, is not null, to identify rows where, like for instance here, to identify rows where the value for the L name column is null, or to identify the rows where the value for the L name column is not null. And finally, the in operator, yeah, with the version not, which can also be prefixed by nothing. The in operator, operation of values placed between parentheses. Now, L name is a string. L name is a string column, so we will delimit one more time. We'll delimit all these values with single quotes. Yeah. So delete from students where L name equals Popescu or L name equals Ionescu. Or delete from students where L name is not in this set of values. All right, so this one, we talked about the ones in black, the filters in black. Now, this one you'll cover at the seminar. SQL provides support for pattern matching via the like operator and the wildcard symbols percentage, which stands for 0 or several arbitrary characters, and underscore for one arbitrary character. And we'll cover these, this one, and this one, as we discuss queries and subqueries. Okay, now one more thing here. Suppose we have this instance of pirates, and we have this update command. Update pirate set ship ID 3, where pname pirate name equals Jack Sparrow. Now let's see. For the first row here, this condition evaluates to true, of course, right? For the second row, in the pirates table, the condition pname equals Jack Sparrow evaluates to false, obviously. What about in the case of the third row? The condition will evaluate to, what do you think? Will it be true or false?
Well, I guess it should be false.
It should be false, right?
Yeah.
I spoke to you?
Me, Barzo Andrei.
Andrei, okay, so it should be false, right? Okay, but
yeah.
Okay, but null, other opinions, other ideas?
Well, because null is undefined or we don't know the value, then how can we decide if it's Jack Sparrow or not?
Just a sec here. Okay. Please tell me your names. Okay, just your first name. Okay, when you start talking, so I know whom I'm speaking to.
Okay, sorry, Philip.
Cum anume? Mai repete, te rog.
Philip.
Repete, te rog.
Philip.
Philip. Yes, that's correct. Exactly. So null denotes unknown. This means we simply don't know. In fact, the pirate name for this pirate in particular could be Jack Sparrow, in which case the condition evaluated to true. It could also be Elizabeth Swan, yeah, or Captain Barbosa, yeah, in which case we would have a false here. So to deal with such cases, we need in fact a valued logic operating with three truth values, that is true, false, and unknown. So in this case here, the condition evaluates to null, that is unknown. We simply don't know. And in fact, the update will affect only the rows for which the condition evaluates to true. That is only this one. So then not true is false, we know this, not false is true, and not null is null, if we apply the same reasoning. And let's look at this instance now. Pirates P1, P2, P3. With this update, set something, we update pirates where? Ship ID equals 1. Well, for the first row, of course, the condition will evaluate to true, right? For the second row, it will obviously evaluate to false. What about for the third row? We have two atoms here. It's this one and this one, yeah, connected by an end. P name equals Jack Sparrow for the third row.
Would it also be null since we
It would be null.
have
It would be null. Now I spoke with
Karina?
Karina, yes, it would be null, yeah? We just explained why. And here, ship ID equals 1 evaluates 2, of course. True, right? Obviously. Okay, so then the entire condition, we have null and true evaluates 2.
Null.
Evaluates to null, of course. Why? Because we simply don't know here. It could be true, in which case we would have true and true with a final result of true, or it could be false, in which case we would have false and true, which would evaluate to false.
My
All right.
question now is, why do we have a null if it acts like a false?
Can you please write it down so you don't forget it, so we get to cover everything? Last time after the lecture, I talked with all the students who asked questions, well, except for one who didn't answer my calls and didn't answer my email either. Dar am răspuns la toate întrebările după curs de la trecută, să apucăm să trecem prin tot. Deci vă rog să notați, bine că e multă materie de acoperit și e pentru licențe, deci nu, în niciun caz nu putem face niciun fel de compromis aici, ca să mai stăm și apoi să acoperim gen mai încolo. Trebuie făcut acum. Deci vă rog să notați, le lămurim pe toate, nu rămâne nimic nelămurit, bine? Și la final, cel mai probabil după curs, astăzi, bine? Discutăm. Dar să răspundeți, vă rog, la apel, ok? De fapt, aproape toată lumea a răspuns, cum am zis, cu o excepție de a trecută. Apropo, tot am ajuns la punctul ăsta, vă rog să încercați să urmați, cum să zic, o ordine, așa, pentru întrebări. Adică, la mine, veniți cu toții pentru întrebări legate de curs. Okay? Dar vă rog pentru seminar să vă direcționați către grupele la care sunteți și la fel pentru laborator. Pentru că eu, spre exemplu, am aproximativ 90 de studenți la laborator, de care mă ocup, bineînțeles, și dacă gen primesc, deci nu e că nu vreau, dar nu e timpul fizic, înmulțiți și voi 200 cu o întrebare gen legată de design. Pur și simplu nu se poate. Dacă se vine la mine cu întrebări de la alte laboratoare, nu reușesc să mă ocup de studenții pe care i-am eu la laborator sau răspund la altă persoană sau omit o întrebare. Deci vă rog, încercați, suntem aici cu toții ca să vă ajutăm, în primul rând la orele de laborator, desigur, trebuie să lucrați în timpul laboratorului și să rezolvați cât mai multe probleme atunci și ce nu se poate rezolva, sigur, după la consultații. Deci, dar asta pe de o parte, bine? Deci în timpul orei și să discutați direct cu profesorul de laborator, e acolo să vă ajute, asta facem toți. Pe de altă parte, să parcurgeți, vă rog, materialul și e ultima paranteză pe care o mai fac pe tema asta, cum spuneam, nu avem timp, să parcurgeți materialele de curs și de seminar pentru laborator, pentru că dacă la laborator, gen pentru design, noi trebuie să reluăm suportul de seminar, pentru că nu e parcurs, din nou ajungem în situația în care nu avem timp, că reexplicăm lucruri pe care le-am mai explicat. Bine, deci vă rog mult. De ce? Ca să meargă lucrurile bine, mai ales în acest context. Bun, cine m-a întrebat, vă rog, își notează și, dacă poate, și îmi și scrie și la final după curs discutăm. All right, so we're going to apply the same reasoning for the or connective. For instance, here, yeah, we have update pirate set to the where pirate name equals Jack Sparrow or ship ID equals 1. So for the first one, obviously, it will evaluate to true. Now for the second one, the first part, this one here, evaluates to, again, as Karina said, null, right? And this one evaluates to ship ID equals 1. Here we have a 2, so it evaluates to false. So now we have a null or a false, which evaluates to
null.
A null, okay? Because again, we simply don't know here. If this one is true, we have true or false, which evaluates to true. But if it's false, we have false or false, which evaluates to false. And for the last one, for the last row here, we have again a null. And we have a true. Ship ID actually equals 1. So now we have null or true. If at least one of the operands is true, of course, the condition will evaluate to true. And keep in mind one more time that the rows that will actually be affected by the update statement, by the update command, are only the rows for which the condition in the where clause evaluates to true. Deci trebuie să evalueze la adevărat. Okay, so we are done with the DDL, create, alter, drop. And now the DML, the data manipulation language, is like in progress. We just finished with inserts, with updates and deletes. We saw a couple of filters that we can use, filter types, illustrated through concrete examples. We talked about the free valued logic, and now we move on to select, to the select statement, which is the core of the DML, the data manipulation language, and it allows us to pose queries over the data in our database, which translates to an understanding of the underlying enterprise or underlying organization, the big entity about which we store data in the database. So SQL queries. And we're going to illustrate our queries on this. We're going to work on this schema. We have researchers, we have papers, and we have author contribution. Okay, the same idea applies about age. We talked about this several times. I want to be able to ask queries of the I don't know, give me all the researchers with who are older than 50 or something like that. And I don't want to deal with not now with date operations, because we should normally we should normally keep the date of birth, right? So to keep our queries simple, to focus on the main elements of a query, we'll work with age. So researchers with RID a key, then we have name, we have the impact factor of the researcher and his or her age. Then we have published papers, PID a key, the title of the paper and the conference. The same thing here. Of course, we would store conference ID as a foreign key and have a separate table conference. But I want to be able to ask interesting queries right now. And saying things like, give me all the papers from the conference with CID 5 is not that interesting, and I don't want to have 4 tables. But obviously we would have a different table here. Conference with conference ID, the name of the conference, and here we would keep only the ID of the conference as a foreign key. All right, and then we have a third table, author contribution, with foreign keys, RID, paper ID, and year, and the composite primary key, consisting of these 3 foreign keys. Meaning that, for instance, researcher R1 has worked on paper P1 in 2018, in 2019, and in 2000.
We can hear you again.
Thank you, I know. All right. All right. So did I get to finish this part? Before the connection dropped, did I get to finish this part here, please?
You were at the 2012. You almost finished saying 2020.
I was sorry?
You almost finished saying 2020 and then it dropped.
Okay, that's great. So what I was saying is that we are storing the fact that a researcher is working on the same paper in several years. Yeah, before I don't know, maybe he abandons, okay, his work, or maybe the paper finally gets published in 2020. Okay, so this is the meaning. This is the meaning of this composite primary key. All right, so let's see a first query, a simple query. Find the names of the researchers who have worked on the paper with paper ID 307. And suppose we have these two instances for researchers and for author contribution. So in this case, we see that we have a 307 here and a 307 here with corresponding researchers RID1 and RID2. That is this one and this one. So the names are Popescu and Ionescu. This should be this is the answer to our question in English. So now we will express this English question in SQL, and it translates to this. We have a select r.name from researchers R, comma, author contribution A, where r.rid equals a.rid and a.PID equals 307. Let's see what this actually means. We will first, to obtain an answer for this query, we will first compute the cross product of tables researchers and author contribution. That is, we have 3 rows here, we have 3 rows here, and 3 rows here. So we'll have a total of 9 rows. The schema of the cross product includes all the columns in researchers. So we have RID, name, impact factor, age, followed by all the columns in author contribution. That is RID, PID, and year. And we take the first row here in researchers. It's 1 Popescu 1030, and we combine it, we concatenate it with each of the 3 rows in author contribution. So we have 1 Popescu 1040, 1 307 2011, then 1 200 2012, and 2 307, that is this one here. I cannot move this row. Oh, okay. It's too low. And then we have 3 rows here for Popescu, 3 more rows for Ionescu, and 3 more rows for Andreescu. All right, then we focus on the where part of the query. That is, we eliminate the rows that don't match this condition here, this expression. Yeah? The first part says that the RID in researchers must be identical with the RID in author contribution. Well, this row, for instance, 1 Popescu 1040 with 1 307 2011 actually makes sense for us. It combines data about researcher Popescu with data about one of the papers that he's been working on. And the same goes for this one here. But this row makes no sense in our particular context. We have data about researcher R1, 1 Popescu nu știu ce, and it's combined with data about researcher R2. So in this case, for this query, it makes no sense, and we don't actually need this row. So we will eliminate all rows that don't satisfy this qualification here. First, we have this atom, r.rid equals a.rid, and then we have this part of the condition, a.pid equals 307. We are interested in only those researchers who have worked on the paper with paper ID 307. And since we have an end, obviously, we will keep only the rows that satisfy both operands of the end connected. Yeah? And in the end, we are left with only 2 rows. That is corresponding to researcher R1 and corresponding to researcher R2. And then finally, the last part, evaluation for the query, we remove the columns that don't appear in the select clause. So in our select clause, we only had the name column. So we eliminate all the other columns, and we'll be left with a table with one column, and in this case, only 2 rows. This will be the answer to our query. All right, so the basic form for a select query, for an SQL query, is as follows. Select from, and you have a from list here. Whoa. From list, where qualification, and you select distinct select list. So select distinct select list from list where qualification. Now these 2 clauses here, select and from, are mandatory. Yeah. So you have a query, you need both select and from, whereas the where clause is optional. Now in the from clause, you have a list of table names. They can be followed by range variables, like we have an R here for researchers and an A here for author contribution. These are aliases that we can use for a table in a query. These are aliases that we can use for a table in a query. Please mute your microphones. So once we introduce a range variable like this one here, R for researchers, we can. Okay, hold on just a sec, please. Okay, I muted you all, okay? Because I think there's someone who forgot to mute their microphone. Okay, so let's go back to the presentation. All right, so once we introduce a range variable like R for researchers, we'll be able to use it to refer to researchers inside the query, in this query. Imagine you have, because here, for instance, RID, this column appears in both tables, in researchers and in author contribution. So if you want to specify an equality condition like this one, you must qualify the column name RID with its table. That is, you could say where researchers.rid equals author contribution.rid. You will see this at the seminar. So if you have a big query with 10 or 12 tables and you have a lot of primary key to foreign key relationships among different tables, then if the table names have, I don't know, 5, 10, up to, let's say, 20 characters, your query will grow a lot. Okay, so then it's a good idea to use such shorter names for your tables. Range variables are in fact only needed when the same relation name appears twice or thrice or multiple times in the from clause. We'll see an example in a bit, okay? So getting back here, the from list is a list of table names, each of which can be followed by a range variable. Now, the select list here is a list of column names or expressions involving column names, and we can only have column names from tables that are named in this from list here. Now, the column names that appear in select can also be prefixed by range variables. In our case, in the select, we have a single column name. And then we have the qualification in the where clause. which is a Boolean combination of conditions that have the form, I'm going to write here, expression, operator, expression, where up is a comparison operator, less than or equal to, greater than, yeah, and so on. And expression is a column name, a constant, an expression, an arithmetic expression involving column names, constants. We can also have string expressions. We can also have expressions over dates. And they are connected. Oh, very sensitive, this one. Okay. And they are connected, I was saying, via AND or and not. Now, the answer to a query is a relation. Now, the answer to this query is this relation here. Now, in the model, we said a relation, in the previous lecture, a relation is defined as a set of rows, a set of tuples, so all the elements are distinct. But in SQL, a relation is a multiset, multiset. That is, it can contain a multiset of rows. That is, it can contain several copies of each row. Multi as well as a set. So these are both unordered collection of elements. But in a multiset, you can have several copies for some elements. So if you want your result set to be duplicate-free, you must specify the distinct keyword. That is, select distinct select list from list where qualification. All right, so we've seen basic queries and we've seen the so-called conceptual evaluation strategy. That is how a query is actually evaluated. We constructed the cross product for the tables in the from clause. Then we applied the qualification in the where clause. And finally, at the end, we retain only the columns that appear in the select clause. Now, I'm going to ask you to be patient. I asked your peers at the seminar yesterday as well. As I said in the first lecture, we have several lectures dedicated to the physical structure of databases, file organizations, indexes, and optimization, and several other lectures devoted to optimization in the second semester. Okay, so we'll deal with optimizing queries, different complexities for our queries and all. No matter the manner in which a system like SQL Server actually evaluates a query, the system should always obtain the result set that it obtains via this conceptual evaluation strategy. That is, by first computing the cross product of the tables in the from clause, then applying the qualification in the where clause, and at the end extracting columns that appear in the select clause. This is the correct answer set for a query, because obviously it makes sense to first apply some part of the qualification in the where clause, right? To reduce the size of the temporary tables and then compute a cross product, okay, or have a join. But we'll talk about this later. For now, we are learning how to write SQL queries, and we are learning what the correct result for a query is. One more time, a subset of the cross product, the rows in the cross product that meet the conditions in the where clause, and from these rows, we only extract the columns that we are interested in. Let's see a couple of examples for basic queries. Yeah, for instance, this one, find the names and ages of all researchers and eliminate duplicates. So here we are extracting a vertical slice from our data table. We're extracting two columns, that is this one and this one. There are no filters, but we also eliminate duplicates. So the result set for this query here will be Ionescu 30 and Andreescu 24. We had 2 copies for this row here, Ionescu 30. One was eliminated because we specified distinct. And let's see another one. Find the researchers with an impact factor greater than 3. So in this case, we retrieve all the columns. We are interested in all the data about researchers, but we're interested in a subset of researchers. So here we are extracting a horizontal slice from our data table. That is these 2 rows here. And we can use this convenient shorthand whenever we want to retrieve all the columns from a table. Select RID, name, impact factor, age, translates to select asterisk or star. Okay. This is another way of introducing the range variable. You can use the optional keyword as. We'll talk about range variables at the seminar as well. All right, now a first query operating on 3 tables. Find the names of researchers who've published in the EDBT conference, a very nice and well-known databases conference. So in this case, we need all 3 tables. We need researchers, papers, and author contribution because we want to retrieve the names of researchers who did this and that, and we are interested in filtering out rows corresponding to papers that are not EDBT. So the name of the conference is in the papers table. And the link among researchers and papers is in the author contribution table. So here we'll have from researchers R, author contribution A, papers B. And then in the where clause in the qualification, we specify these join or link conditions. Yeah, the RID in researchers and the RID in author contribution must be identical. And this one here, the paper ID in author contribution and the paper ID in papers must be identical as well. So for this row here in researchers with RID1, we have 2 matches, this one and this one. And this one has a PID of 1, so it corresponds to this row here. And this one has a PID of 7, so we will link this row with this one here. And then we'll also apply this part of the qualification. So conference equals EDBT. Well, for the second paper with PID 7, conference is IDS, another good conference on databases, but we are not interested in this one right now. So we'll only keep the row corresponding to the EDBT conference. So we'll have a big row with this schema: RID, name, impact factor, age, RID, PID year, PID title conference, and a single row: 1 Ionescu 1030, 1 2011, 1 T1 EDBT. And then for this researcher here, we have 2 matches in author contribution, this one and this one, PID 7 and PID 9. So we have these 2 matches here. 7 is in IDS, so we don't care about this paper, whereas 9 is in EDBT. So we will keep this row as well. So we'll have another row in the cross product for this researcher 2, Popescu 1040, 2, 9, 2019, 9, title T3 EDBT. So we have 2 rows in the cross product. And then from these 2 rows, because for Andreescu, for RID4, there are no rows in author contribution. And then from these rows here, we're going to simply extract the name. That is, in the final result set, we'll have a table with 1 column name and 2 rows, Ionescu and Popescu. And in the same manner, we can have a cross product of 4 tables, of 5 tables, and so on and so forth. Now, if we are only interested in the IDs of researchers who have published in this conference in EDBT, we can omit the researchers table because we have the researcher ID information in author contribution. So it's enough to compute the cross product of author contribution and papers, add this join condition on paper ID, and this filter on the name of the conference and retrieve the researcher ID. All right, now suppose we are interested in the names of researchers who published at least 1 paper, not at least 2 or 3. For this purpose, we'll use a different construct. but at least one paper. Well, then it's very simple to solve this query to come up with a correspondent in SQL. We simply join researchers with author contribution. We construct the cross product, and then we apply this condition, an equality on the researcher ID in the two tables. Because if a researcher did not publish in EDBT, then the second step in the conceptual evaluation strategy, that is where we apply the qualification in the where clause, would eliminate all the rows about this researcher. Yeah. We have, for instance, 1 match with 1, 1, 2, 2 in the cross product, then 2 match with 1, 1, 2, 2 in the cross product, and 4 matched with 1, 1, 2, 2 in the cross product. Yeah. But while Ionescu and Popescu will be retained in the answer set because we have equalities here, 1 with 1, 1, and 2 with 2 and 2. The 4 rows corresponding to 4 Andreescu 224 in the cross product will be eliminated because there are no matches in author country. There's no rows with RID4. Bun. We'll take a short break now. Vă rog să vă puneți microfoanele pe mut. Bine? Nu îmi place să vă pun eu pe mut sau ceva de genul. Bine? Vă rog frumos, ok? Alright, so continuăm după pauză. All right, let's continue. Now, a query that is very similar to the previous one, to a previous query, we are selecting the conferences that published Ionescu's papers. So it's very similar, only that now we are not filtering rows based on the name of the conference, we are filtering rows based on the name of the researcher. We have the same cross product and then the same join conditions. And in the end, we select only the conferences names. Now, of course, we could have more than one researcher with this name, right? Ionescu. So this query actually returns the names of the conferences that published Ionescu's papers for all researchers named Ionescu. Yeah. But if the name is a key, then we'll have a single researcher, or at most one researcher with this name. All right, now let's write a query ourselves, and that we can use it to illustrate the fact that in the select clause we can have expressions, yeah, involving column names and constants. So compute an incremented impact factor for researchers who worked on 2 different papers in the same year. So 2 different papers in the same year. That is, for instance, for a researcher, let's say R1 with a name and I don't know what else, we should have R1, P1, let's say 2020, and R1, P2, 2020. We should find 3 such tuples, 1 tuple in researchers and 2 tuples in author contribution with the same researcher ID, the same year, and different paper IDs. Let's see how it would go. We'll select from. Well, we have researchers, R, and then we have author contribution, A1, and author contribution, A2, where R dot RID equals A1 dot RID and R dot RID equals A2 dot RID. That is, we are using, so in this case, this is the first example of a query in which we actually, we have to use range variables because we have a table appearing multiple times, in this case, twice. So we need to be able to distinguish between these 2 occurrences of author contribution. So we have the cross product of researchers, 1 instance of author contribution, and a second instance of author contribution. So we'll have a big row, RID, R name, age, and so on. RID, PID, year from A1. RID, PID, year from A2, from author contribution A2. And we'll keep only those rows with the same RID in researchers, in author contribution A1, and in author contribution A2. Moreover, so we have same year, right? And A2. A2 dot PID. That is, in this big row, yeah, the year from author contribution A1 is identical with the year from author contribution A2. Sorry, and the paper IDs are different. The 2 PID values are different, meaning that the current researcher has worked on 2 different papers in the same year. And then for this researcher, we can simply retrieve, I don't know, maybe his ID, maybe his name. And we said we would compute an incremented impact factor. That is R dot, it was impact factor. Impact factor +1. Yeah. And we can also assign a name to this column. So as, like new impact factor, for instance, using the optional keyword as. So the result set will have 3 columns named RID, name, and NIF, new impact factor. All right, now we continue with nested queries. Now in SQL, this is a very powerful feature of SQL. In SQL, a query can have another query that's embedded within it, like in the where clause, in the from clause, and we'll later see in the having clause, and in the select clause. We'll start with nested queries that have subqueries embedded in their where clause. We have the same English question. Now find the names of research, or statement in this case, find the names of researchers who worked on the paper with PID 307. And now we will rewrite it using a nested query with the in operator. In allows us to test whether a value belongs to a given set of elements. We've seen an example in which after in, we have parentheses and an enumeration of actual values. Well, in this case, the set that we want to test is generated with a SQL query. Like here, we are selecting from author contribution, where the paper ID is 307, the corresponding RIDs. So these are the set of researcher IDs for the researchers who have worked on the paper with PID 307. So this happens in this subquery. And then in the top level query, in this one here, we are selecting only those researchers, their names that is, for which the RID is in this computed set of RIDs. So 1, 4 here. We'll take the first row here. Is RID in 1, 4? It is. Then this row will be part of the result set. We'll take the second row with a value of 2 for the RID. Is RID in 1, 4? No, it's not. So this row won't be part of the result set. This one will. Yeah, RID 4, it's in 1, 4. So then the result set will include Ionescu and Andreescu. Now, of course, you can have multiply level nested queries. Like in this case here, we want the names of researchers who've published in EDBT. That is, this subquery here has another subquery in its own where clause. The inner query here, the innermost query, computes the set of paper IDs, PIDs, for the EDBT conference. That is, we have a 1 and a 9. Then the query one level above, this one here, computes the set of researcher IDs for the researchers who have worked on a paper whose PID is in this set. That is 1 and 9. So we have a 1 and a 2. And finally, the top level query retrieves the names of the researchers with an RID in this set. That is 1 and 2. So we have Ionescu and Popescu. And then you can say things like find the names of the researchers who have not published in EDBT. You simply replace the outermost occurrence of in by not in. Or you could replace this occurrence of in with not in which case here you would retrieve the IDs of the researchers, so where PID not in, who have worked on a paper that is not EDBT. And then the names of the researchers whose RID is in this set. Or you could replace both occurrences of in with not in which case you would obtain the names of the researchers who have not worked on a paper that is not EDBT. You can play around with such a query and experiment a bit, okay, on your own instances. All right, so now in the previous version of the query, so within this one here, this subquery is completely independent of the outer query, of the current row that we examine from this query here. Yeah. We'll always have the same set of RIDs here, 1 and 4. We can also write correlated queries, that is queries with correlation, using the exists operator. Like find names of researchers who worked on the paper with paper ID 307, same statement, only that now, for each row in researchers, we check whether there are rows in author contribution with a PID of 307 and the same RID. That is, for instance, for 1. We check, are there any rows in author contribution with PID 307 and RID 1? Yes, we have this row. In this case, this query here will return a non-empty answer set, in which case exists returns true. So exists allows us to test whether a set is non-empty. If the set is not empty, exists returns true, then the qualification is satisfied, and we'll have a row in the result set for this row here. That is, we'll keep Ionescu in the result set. Then we continue with the next row in researchers, 2, Popescu, 10, 40. So let's see, are there any rows in author contribution with researcher ID 2 and paper ID 307? There are no such rows, so this won't be part of the result set. And finally, 4, yeah. And we have a row in author contribution with RID 4 and PID 307. So we'll have Ionescu and Andreescu. This is called the correlated query. This here is called the correlation, the occurrence of R in this subquery here. All right, so we discussed about operators in and exist. Now there are 2 other operators, set operators, which allow us to compare a value with the elements in a given set using a comparison operator, an arithmetic comparison operator, greater than, less than, and so on. Let's take this statement. Find researchers whose impact factor is greater than the impact factor of some researcher called Ionescu. Some researcher called Ionescu. Well, for instance, if we have this instance, we have 2 Ionescu here with an impact factor of 10 and 11. Okay, so let's see. Andreescu, is his impact factor greater than any of 10 and 11? Well, no, it's equal to 10. So this won't be part of the result set. What about Vladescu? Well, yeah, the condition is then true because 11 is greater than 10. Deci să fie mai mare decât oricare, greater than any of the values that we have in our set. And the same goes for Mușatescu. Okay, so to compute this result set, we can write it with the any operator. We'll retrieve the IDs of the researchers for which. I'm sorry, your colleague Constantin Onciu has requested control for this presentation, so I had to stop a bit. So from researchers R, yeah, where impact factor is greater than any of, and then we have a subquery that computes this set here, yeah, from researchers R2, where R2.name equals Ionescu, we select the impact factor that is 10 and 11, and then in the query one level above him, the top level query, we iterate over all the rows in researchers and simply evaluate this condition. We check and see whether the impact factor of the current row is greater than at least one of the values in the computed set of impact factors, which translates to greater than the minimum value. Now we have this equivalence here. Expression equals any of subquery is equivalent with expression in subquery. It's the same thing. For instance, here, yeah, we are selecting the names of the researchers where the researcher ID is in this set. This is the set of researcher IDs for those who have contributed, who have worked on the paper with PID 300. And you can rephrase this, you can reformulate this in SQL like this. Researcher name from researchers R, where r.rid equals any, and then you have, it's exactly the same subquery. Yeah. A similar operator, similar in that the syntax is basically identical. It allows us to find researchers whose impact factor is greater than the impact factor of every researcher called Ionescu. So in this case, Andreescu, of course, doesn't satisfy the condition, and neither does Vladescu, because 11 is not greater than all the values in this set. Mușatescu does satisfy the condition. And then the query is identical except for the use of all rather than any. Yeah, give me all the researchers from RIDs from researchers where the impact factor is greater than all. And here we have the subquery computing the set of impact factor values for the researcher named Ionescu. All right, and then we have this equivalence expression different from all of subquery is equivalent with expression not in subquery. So if you want to retrieve the names of the researchers who have not worked on the paper with PID 300, you can either say where RID not in, and here you have the set of researcher IDs from author contribution for those researchers who contributed on the work on the paper with PID 300, or you could say where researcher ID different than all, and you have exactly the same subquery. All right, so we covered basic queries. We extracted a horizontal slice from a table, a vertical slice, their intersection as well. We made sure our result set is in fact a set by applying the distinct keyword. Okay, only if we need this feature. Okay, if we don't, if a multi-set is fine for us, we don't specify distinct. Distinct eliminating duplicates is quite an expensive operation, as we'll later see. We dealt with queries operating on a single table, on two tables, on three tables. And then we discussed nested queries. That is queries with queries that contain another query. We saw such subqueries in the where clause. And we covered the following set operators. N, one more time, it allows us to test if a value is in a set. In our case, the set that we tested was generated with an SQL query. Exists, which we use to test if a set is not empty, and any and op any and op all, which we can use to compare a certain value with all the elements in a set generated by a SQL query, with all the elements in a set using one of the arithmetic comparison operators. All right, so now we can move on. And we'll discuss union, intersection, and set difference. Now, at the seminar, you will cover 3 set manipulation constructs in SQL that implement these operations. That is union, intersect, and except. Yeah? Now we'll see how we can write queries with such operations if these operators are not in our extension of SQL. Well, now they basically are, but suppose they are not. We don't have these operators. We can still express the corresponding queries, yeah? Like find the names of researchers who've published in EDBT or ideas. Now, we have the OR connective in the English statement. We'll use the same OR connective in the SQL version of the query, of the question. So we're selecting name from researcher author contribution papers with the same link conditions, the same join conditions, and we are saying that the name of the conference can be ideas or the name of the conference can be EDBT. It's quite straightforward. This one's easy. And now suppose we have this statement in English. So find the names of researchers who have published in eDBT and ideas. So this corresponds to the intersection operation. So then in the English statement, we simply replace the or with and. So then we can do the same thing, right? In the SQL version of the statement. Well, of course, we cannot. Yeah, we cannot do it. Well, why is that? Because when you say something like this, p.conference equals ideas, and p.conference equals eDBT, you're saying that one name here for a conference for a particular paper, because PID is a key, should be equal with ideas and with eDBT at the same time. Now, PID is a key, so one value here, which is atomic, cannot be both eDBT and ideas. It's either eDBT or ideas. So if you write such a query, you will be able to execute it. It's syntactically correct. However, the answer set will always be empty. You'll always get an empty answer set. So then in this case, we can write, if you don't use the intersect operator, we can write such a query. It uses the same idea that we have seen before when we used author contribution twice in the from clause. So now we are looking for what? We are looking for 5 tuples in researchers, in author contribution A1, in papers P1, in author contribution A2, in papers P2, such that we have the same researcher ID in researchers, author contribution A1 and author contribution A2. That is, all the tuples refer to the same researcher. We have this filter here, and there's another one here. Then the PID in A1 is equal with the PID in P1. That is this one here. And P1.conference equals ideas. So if we have these 3 tuples, one in researchers, one in author contribution A1, and one in papers P1 with a conference ideas, this means that the current researcher has an ideas paper. And then we are looking for 2 more tuples, author contribution A2, papers P2, with equal PIDs here. So A2.PID equals P2.PID, and a conference of eDBT. So if we have 5 such tuples, one in researchers, 2 in author contribution for this researcher, and 2 more in papers for the same researcher, one with a paper of eDBT and the other one ideas, this means that the researcher has published in both eDBT and ideas. And if you want to say, give me the researchers who have not published, who have published in eDBT but not in ideas, well, the first part of the query, we've seen it before, computes the names of the researchers who have published in eDBT, and we add this condition with another subquery in the where clause, and the RID of the current researcher is not in. And here, in the subquery, we compute the set of RIDs for all the researchers who have published in ideas. So then the top-level query retrieves the names of the researchers who published in eDBT, but not in ideas. All right, now let's continue with the join operators. We've seen before that we compute a cross product like of 2 tables in the from clause, and then we specify a condition that combines data from these 2 tables. Well, since such an operation is quite fundamental in the relational model, it's used very often, yeah, because we need to combine data from different tables. In fact, we have a dedicated operator. It's the join operator, and it has 4 versions: inner join, left join, right join, and full join. Now, suppose we have these 3 instances for students with student ID a key, for courses with course ID a key, and for exams with the student ID and the course ID, with the corresponding grade and number of credits. And we'll see 4 queries now. Suppose we want to find all the students' grades, and we also need the names of the students in the answer set, because we can take the grades, okay, from exams. But if you also want to have the names of the students in the answer set, you need students as well. So one option is you write select from students, comma, exams, where, and you have the link condition. Another one is and you obtain exactly the same result set. Another one is to use the special inner join operator. And the syntax is like this. From students as inner join, or simply join. Inner is optional. Inner join exams E. And then you have on followed by the join condition, which combines the data from the two tables. So then here we'll have 135 Alexandra from 922 combined with these two rows. 135 BD 10, 135 DBMS SGBD, ZEC, and so on. And then for Paul, with ID 82 here, we have one match in exams. So we'll have 82 Paul Node 926, 82 SGBD 10.6. So this is the result of the inner join. It's basically cross product with the filter consisting of a join condition, combining the data in the two tables. All right, now, suppose that we want to find all the students' grades and we want to see the students' names as well, but the answer set should also include students with no exams. Students with no exams, okay? Maybe someone forgot to introduce their grades, and then we need to see this and we need to say, okay, please introduce the grades for all the students. Well, then we will use the left join operator. Select from students, left join exams on, and we have exactly the same join condition as before. So then this means that we'll have the result set of the inner join. So again, 135 Alexandra with her two results, and 82 Paul with his result. And we'll have one more row for Stefania here from 925, so 294, Stefania 925, combined with null values for all the columns that come from the right operand. So 294, Stefania 5, null, 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 because she has no grades, right? But we still want to see her in the result set. And then we have the symmetric operation right join, which is similar to the left join, only that now we consider the right operand. So it's exams, right join courses, and then this means that we have the result set from the inner join plus. We go and we examine every row in courses, and if we have rows with no match in the left operand, that is exams, we'll simply add them to the result set with null values for all the columns that come from exams. So we first have the inner join of exams and courses. This means we have all the columns from exams. So SID, course ID, grade credits, followed by all the columns from courses. So CID name. CID name. We compute the inner join first. Okay, so we have 3 rows here. 135, 135, 82 with BD and SGBD. That is base de date and sistema de gestione a baselor de date. And then we notice that we have one row in courses. Courses is the right operand for this right join operator here. We have one row in courses, DMBD data mining in big data, with no match in exams. So we'll add this row to the result set and we'll use null values, that is unknown, for all the columns that come from the left operand, that is exams. And then we can go and say, okay, hey, did you introduce all the grades for DMBD? I see no grades in the database. Is there an error? What's going on? Or maybe you didn't have the exam yet. So this is the right join, another version of the join operator. And finally, the last one, this one is the full join. It combines result sets obtained with the left and the right join. For instance, we want to see data about all the exams. We want to include students with no exams, and we want to include grades given by mistake to students that don't exist in the database, like this one here, which means that STD-ID cannot be a foreign key in exams. Okay, so we forgot to declare the foreign key, and someone introduced erroneous data here, data about a student that doesn't exist in our database. All right, so then we use the full variant of the join operation. Full outer join or full join, the same thing. Left outer join or left join, the same thing. Right outer join or right join, again, the same thing. So we first compute the inner join, just like before. It corresponds to the first 3 rows here. Yeah, all the columns in students, this one, and this one, followed by all the columns in exams, this one, and this one. Yeah, 135 with 135 and 135, the first 2 rows, 82 with 82, this one, this row here. And then, so this is the inner join, the result of the inner join. And then to this result set, we add 1 row for every row in the left operand in students for which we found no match in the right operand in exams. We have 1 such row, it's this one. So 294 Stefania 925 with null, 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 null. It's the row that we obtained when computing the left join. And then we examine the right operand, so exams. We see that we have only one row with student ID 737 with no matching rows in students. So we'll add it to the result set and we'll use null values for all the columns that come from the left operand. So depending on our needs, we can use one of the four join operators. One more time, combine the data from different tables. All right, now that we have seen the join operator, so from now on, we will always write queries that combine data from different tables. We will always write them with joins, okay, not with cross products followed by qualifications in the where clause. We'll see why. We'll see the importance of the cross product in a subsequent lecture on relational algebra when we discuss about an independent set of operators. Okay, so but for now, every time we have a condition combining data from different tables, we use a join. So now that we have seen the joins, we'll give an example of a nested query that has a subquery, not in the where, but in the from clause, but written with a join, okay, not with a cross product. So for instance, here we are selecting data about researchers who worked on the paper with paper ID 400 in this manner. We are joining a table, researchers are, with, well, it's another table identified via this alias T, but this table here, the second one, is a computed table, the one that is computed as part of the query using a subquery. Here we are selecting, so between parentheses, yeah, we are selecting all the rows in author contribution where paper ID is 400. So we will know all the researchers who worked on this particular paper, and the schema of this table T will be identical with the schema of author contribution. So RID, PID, and year. So we'll have, in fact, 2 tables in the join, R and T, and we can establish a link condition between them. R.RID equals T.RID. We join researchers with T using this equality condition on the researcher ID, so that we can retrieve data about the researchers who've worked on the paper with PID 400. And here is another useful shorthand, because the final result, if it's an inner join, the final result will have all the columns in researchers followed by all the columns in T, which are all the columns in author contribution. And if you're only interested in the columns that come from researchers, so in data about researchers, and you don't want to enumerate all of them, here we have only 4 or 5, but if you have a table with 20 columns, that can be quite tedious, okay, to enumerate all of them, you can use this shorthand. So alias dot star, that is all the columns from researchers.
Hi, I am Storm. I break the walls and I take control. You can stop me. Hi, I am Storm. I break the walls and I take control. You can stop me.
All right. Now, again, let me remind you, please write, if you have questions, please write them down and we'll talk after the lecture today, okay? So let's see another type of query. Find the age of the youngest researcher for each impact factor. Find the age of the youngest researcher for each impact factor. That is, for instance, here, I have two values for the impact factor. It's a 10 and a 2. So I'd like to see something like 10 and 40 and 2 and 24. So one option is we can go and we can write queries of the form select from where impact factor equals 10. And then another one, select from where impact factor equals 2. And we'll see how we can get the age of the youngest researcher in a bit. So, but obviously this is quite tedious. Okay, we won't do it. We will write a single query that groups the data in our table based on the impact factor values, and then for each impact factor value computes the age of the youngest researcher. Now you have these aggregation operators in SQL: count, average, sum, min, and max. Yeah. Count is very interesting because in fact there are multiple ways in which you can count the values or the rows. For instance, if you say count all, and suppose you have, so select count all from, or maybe researchers, and suppose you only have two columns in researchers, I don't know, column A, column B, and you have null, 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 something like this. Then count all will return 4 because it counts all the rows in the table. But if you replace this one with count A, and this one will return 0, because when you use a column name as an argument to count, count actually counts the number of non-null values for the column. It counts the number of non-null values for the column, and in this case, that number is 0. If we add another one and say Popescu, then count of A will be equal to 1. Add another one, Popescu, count of A will be equal to 2. And if you change this one to count distinct A, sorry că e un pic cam urât, dar aici nu, dacă apăs cu mâna în partea asta, mi se închide. So count of distinct A counts the number of distinct values in column A. In this case, it will return 1. There's a single value, in fact, Popescu. Okay, so then this is how our query would look like. We extend the basic query form with the group by clause, group by, which means that the system will first will build groups of rows where a group of rows has identical values in all the columns that appear in the group by clause. In this case, we have a single column, impact factor. So this is the first group of rows with 10, 10, and this is the second one with 2, 2. And then for each group of rows, it will build a single result row. So for this group here, we will have a single row in the result with, I decided to take the impact factor, that is 10, and min of r.h, min of r.h. That is, min is applied to these values here, and the result is, of course, 30. And then for this group here, for the second one, we'll have another row in the result set for which we'll take again the impact factor, that is 2, and we apply min on r.h, that is, we'll have a 24. Let's see another one. Find the age of the youngest researcher who is at least 18 years old for each impact factor with at least 3 such researchers. Find the age of the youngest researcher who is at least 18 years old for each impact factor with at least 3 such researchers. That is, at least 3 researchers who are at least 18 years old. So the first thing we're going to do is that we're going to filter out rows corresponding to researchers who are younger than 18. And we have this one here, and then we have, okay, and the rest of it, it's fine. Then we'll group the data based on impact factor. because we wanna obtain some aggregated results for each impact factor, yeah, that meets a certain condition. So we have a 5 here. This is one group. Then this is another one. Remember, we eliminated this row. Then this is another one for impact factor 7, and finally the last one. All right. Now we want to see some aggregated data only for those impact factor values for which we have at least 3 such researchers. In our case, 3 researchers because we already got rid of the researchers who are younger than 18. So let's see. For this group here, the condition is not satisfied because we only have 1 row. For this group here, the condition is not satisfied either. We only have 2 rows. But for this one and for this one, this condition that the group should have at least 3 such researchers is satisfied. So then for these 2 groups in the output, we'll have these rows. So find the age for each impact factor with at least. So we're going to take the impact factor, that is 7. And the age of the youngest researcher who is at least 18 years old. So in this case, we'll have 25 and 10 with a 19. And let's see the corresponding query. Yeah. From researchers R, where r.age greater than or equal to 18. So we eliminate the rows, we compute a cross product of the tables in the from clause. In this case, we have a single table, so it's easy. There's no cross product to compute. We eliminate the rows that don't satisfy the qualification in the where clause. Okay, and then we don't go to the select clause, we continue with the group by clause. We group by the impact factor. Yeah, we had these groups here, 4 groups. One more time. Each group has a set of rows with identical values in the columns appearing in the group by clause. And then we have another, so these are optional, these 2, we know this. Then we have another optional clause, namely having. We used where to eliminate rows that don't satisfy a condition. And now we'll use having to eliminate not rows, but groups that don't satisfy a condition. Am folosit where să eliminăm rânduri care nu satisfac o condiție. Acum folosim having să eliminăm grupuri întregi care nu satisfac o condiție. And then the having clause merely states that count all should be greater than 2. So count all here will be applied on each and every group. So we'll take this group here. Count all evaluates to 1. There's a single row in this group. 1 is less than or equal to 2. So obviously the condition is not satisfied. This group is eliminated. Okay, then count all is applied again on the second group. Count all evaluates to 2 for this particular group, which is not greater than 2 here. So this means that this group is eliminated as well. Finally, count all when being applied to this group evaluates to 4, and when being applied to this group evaluates to 3, which are both greater than 2. So these 2 groups, the last 2 groups, qualify. Okay, so one more time. We build a cross product of tables in the from clause. We eliminate rows that don't satisfy the conditions in the where clause, the big qualification condition in the where clause. We group the remaining rows according to the column or columns that appear in the group by clause. We build groups. For now, just at the logical level, okay? We'll later see how groups are actually built at the physical level. That is either by sorting the rows or via hashing. Okay, and then if we have a having clause in our query, we apply the having clause. We apply the qualification condition in the having clause to each and every group. And then we are left with only the groups that that satisfy the qualification condition in the having clause. And for those groups, we will build one row per group in the result set of the query. And we'll take the impact factor and the minimum age. The impact factor and the minimum age. Now, just an observation here. If you have, for instance, select from, I don't know, where, whatever, group by, column, let's say column A, okay? you can select A, and you could select, I don't know, min of B. For instance, you have A, you have B, and you have 1, 1, and let's say 2, 2, 2. This is one group, this is one group. And let's say 1, 2, and let's say 1, 2, 3. Okay, so if you group by A, you can select A in the result set. One more time, keep in mind that in the result set, you will have one row per group. It's very important. Un rând pe grup în rezultat. You can also select min of B or max of B, the maximum value of B, or average of B, the average of all the values that appear in the B column, or sum of B, the sum of the values that appear in the B column. This is fine, but you cannot select B. Yeah? You cannot say select A, B, group by A. Why is that? Well, because you can select A because you group by A. So all the rows in this group will have the same value for A. All the rows in this group will have the same value for A. But this doesn't happen for the other columns. Yeah, for B, for instance, in this case, we have two different values. And in the result set, we must have a single value for this group. We have a single row for this group with a value of 1 for A. So then for B, what value should we choose? Is it 1 or is it 2? And why? Obviously, we cannot decide, okay? You cannot build a correct result set in this manner. So if you group by A and B, then you can select A and B, or one of them, or both, yeah? But you cannot select C. If you want to use C, column C, in the select clause, it must be an aggregate to, it must be an operand to an argument to an aggregation operation. Like you can compute min of C, because for a group, for a given group, min of identified by columns, defined by columns A and B, for a given group, min of C will evaluate to a single value. All right, so that is it for today. Vă aștept cu întrebări acum. I'm waiting for you to ask me questions now. Să urmăriți site-ul facultății, vă rog. Acolo se va pune programul de consultații, dar noi stăm acum și lămurim ce nelămuriri sunt, dacă sunt, după acest curs. Deci vă aștept aici pe Teams, ok? O să închid meeting-ul ăsta și vă aștept aici. Îmi scrieți, vă rog, ok?
Sigur, o zi bună.
Bon, so să aveți o zi, have a nice day and everything, and see you at the next lab/seminar/lecture. Bon, bye everyone.
Bye.
Goodbye. Have a nice day.
Have a